According to the National Electrical Code, NEC Section 250.104a, metal raceways, enclosures, and other metal non-current carrying parts of electrical systems connected to grounded service-neutral conductors must be bonded. NEC Section 250.104c specifies that isolated metal raceways, enclosures, and other metal non-current carrying parts must be bonded to the service equipment enclosure. In the case of PVC-coated 90s and additional vertical conduit GRC that are protruding from the ground and connected to grounded enclosures, they are considered isolated metal raceways. Therefore, they must be bonded to the enclosures. This bonding ensures proper grounding and prevents the accumulation of stray voltages, which could pose a safety hazard. When it comes to methods of bonding, regular Meyers Scru-Tites are not approved for bonding isolated metal raceways because they don't provide a reliable electrical connection. STGs, which stands for Surface Bonding Grounding Devices, are specifically designed for bonding isolated metal raceways and enclosures. They provide a secure and listed electrical connection for this particular purpose. Because the 90s are coated and protruding at least 4 feet out of the ground, the vertical conduit GRC is considered to be isolated. To prevent the accumulation of stray voltages that could create a shock hazard, it must be bonded. Consulting with the local inspector is advisable to confirm the bonding requirements and to inspect the installation. Involving the inspector early can help avoid potential conflicts or delays. Based on the NEC and industry standards, the position that the PVC stub-ups and vertical conduit GRC must be bonded to the enclosures is correct. This is an essential measure for safety and compliance with electrical codes. Therefore, the NEC requires bonding to ensure safety and prevent electrical hazards associated with isolated metal parts. Let's break down the key NEC sections related to this topic. NEC Section 250.45 addresses bonding of electrical equipment. This section emphasizes the need to create a low impedance path for fault current to facilitate the operation of overcurrent protective devices. The intent is to ensure that in the event of a ground fault, the fault current will quickly trip a breaker or blow a fuse, thereby minimizing the risk of electrical shock or fire. Proper bonding helps to achieve this by providing a reliable path for the fault current to flow back to the source. NEC Section 250.92 pertains to bonding of metal enclosures containing service conductors. Service conductors are the conductors that bring power from the utility company to the building. This section requires that metal enclosures, such as conduits and cabinets containing service conductors, be bonded together into the grounding electrode system. The purpose of this bonding is to minimize voltage differences between the enclosures and the ground, which can reduce the risk of electrical shock. NEC Section 250.96 covers bonding of other enclosures. This section expands on the requirements of Section 250.92 to include metal enclosures containing other than service conductors. It requires that these enclosures be bonded to the equipment grounding conductor. This ensures that all metal enclosures in the electrical system are properly grounded and bonded, providing a safe path for fault current. NEC Section 250.102 specifies the wiring methods for bonding. This section outlines the acceptable methods for connecting bonding jumpers and equipment grounding conductors. It allows the use of various types of connectors, such as lugs, pressure connectors, and exothermic wells, as long as they are listed for the purpose. It also specifies the minimum size of bonding jumpers based on the size of the circuit conductors. NEC Section 250.104, as previously mentioned, focuses on bonding of piping systems and exposed structural metal. This section requires that metal water piping systems and exposed structural metal that are likely to become energized be bonded to the grounding electrode system. This bonding helps to prevent electrical shock hazards that could arise if these metal parts become energized due to a fault in the electrical system. The reason why regular Meyers Scru-Tite connectors are not suitable for bonding isolated metal raceways is because they do not provide a reliable, low-impedance connection. These connectors are typically designed for mechanical connections rather than electrical bonding. Over time, the connection can loosen or corrode, which increases the impedance and reduces the effectiveness of the bonding. STG connectors, on the other hand, are specifically designed and listed for bonding metal raceways. They provide a secure, low-impedance connection that is resistant to loosening and corrosion. These connectors typically use a compression-type connection that ensures good electrical contact between the connector and the raceway. The importance of consulting with the local electrical inspector cannot be overstated. Electrical inspectors are responsible for enforcing the NEC and other local electrical codes. They have the expertise to interpret the code and ensure that electrical installations are safe and compliant. By involving the inspector early in the process, potential problems can be identified and corrected before they lead to costly rework or safety hazards. Firstly, proper bonding of metal conduit risers is essential for electrical safety and compliance with the NEC. Secondly, regular Meyers Scru-Tite connectors are not suitable for bonding isolated metal raceways due to their unreliable connection. Thirdly, STG connectors are specifically designed and listed for bonding metal raceways, providing a secure, low-impedance connection. Fourthly, consulting with the local electrical inspector is crucial to ensure compliance with the NEC and to identify potential problems early on. Firstly, grounding and bonding are fundamental concepts in electrical safety. Grounding refers to connecting electrical equipment to the earth, providing a path for fault current to flow back to the source. Secondly, bonding involves connecting metal parts of the electrical system together to create a continuous electrical path. Thirdly, the purpose of grounding and bonding is to minimize voltage differences between metal parts and the earth, which reduces the risk of electrical shock. Fourthly, the NEC contains extensive requirements for grounding and bonding, which are designed to ensure the safety of electrical systems. The NEC defines an equipment grounding conductor, or EG, as the conductive path installed to connect normally non-current carrying metal parts of equipment to the system grounded conductor, the grounding electrode conductor, or both. The purpose of the EGC is to provide a low-impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. The EGC can be a wire, a metal raceway, or other approved conductive path. The grounding electrode conductor, or GEC, connects the system grounded conductor to the grounding electrode. The grounding electrode is typically a metal rod, pipe, or plate that is buried in the earth. The purpose of the GEC is to provide a direct connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault current to dissipate. The NEC specifies the minimum size of the GEC based on the size of the service entrance conductors. A bonding jumper is a conductor that connects metal parts of the electrical system together to create a continuous electrical path. Bonding jumpers are used to bond metal conduits, metal enclosures, and other metal parts to the equipment grounding conductor. The purpose of bonding jumpers is to minimize voltage differences between metal parts and to provide a low impedance path for fault current. The NEC specifies the minimum size of bonding jumpers based on the size of the circuit conductors. The main bonding jumper connects the equipment grounding conductor to the system grounded conductor at the service equipment. The purpose of the main bonding jumper is to provide a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. The NEC specifies the minimum size of the main bonding jumper based on the size of the service entrance conductors. Supplemental grounding electrodes are grounding electrodes that are installed in addition to the required grounding electrode. Supplemental grounding electrodes are often used to improve the grounding of electrical systems in areas with poor soil conductivity. The NEC allows the use of supplemental grounding electrodes, but they must be bonded to the equipment grounding conductor. Impedance is the opposition to the flow of alternating current in an electrical circuit. Impedance is similar to resistance in a direct current circuit, but it also takes into account the effects of capacitance and inductance. A low impedance path is essential for effective grounding and bonding. A low impedance path allows fault current to flow quickly back to the source, which helps to ensure that overcurrent protective devices operate and clear the fault. Voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Voltage drop can be a problem in long circuits or circuits with high current loads. Excessive voltage drop can cause equipment to malfunction or overheat. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders. Stray voltage is unwanted voltage that can appear on metal parts of the electrical system. Stray voltage can be caused by a variety of factors, including poor grounding, inductive coupling, and capacitive coupling. Stray voltage can be a shock hazard and can also interfere with the operation of sensitive electronic equipment. Equipotential bonding is a technique used to minimize voltage differences between metal parts in an area. Equipotential bonding involves connecting all metal parts in the area together with bonding jumpers. This helps to ensure that all metal parts are at the same voltage potential, which reduces the risk of electrical shock. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the current if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or AFCIs, are devices that are designed to protect against fires caused by arc faults. Arc faults are unintentional electrical discharges that can occur in damaged or deteriorated wiring. AFCIs detect arc faults and quickly interrupt the current, preventing a fire from starting. AFCIs are required in many locations, such as bedrooms and living rooms. Surge protective devices, or STGs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. STGs divert the surge current to ground, protecting the equipment from damage. The National Electrical Manufacturers Association, or NEMA, is a trade association that represents manufacturers of electrical equipment. NEMA develops standards for electrical equipment and provides information and education to the electrical industry. Underwriters Laboratories, or ALL, is an independent testing laboratory that tests and certifies electrical equipment. UL listing indicates that the equipment has been tested and meets UL safety standards. The Institute of Electrical and Electronics Engineers, or IEE, is a professional organization for electrical and electronics engineers. IEE develops standards for electrical and electronics engineering and provides information and education to the electrical industry. The International Association of Electrical Inspectors, or IE, is a professional organization for electrical inspectors. IE provides education and certification for electrical inspectors and promotes electrical safety. Firstly, always follow the NEC and other applicable electrical codes. Secondly, use listed equipment and materials. Thirdly, properly ground and bond all metal parts of the electrical system. Fourthly, install GFCIs in required locations. Fifthly, install AFCIs in required locations. Sixthly, install STG to protect against voltage surges. Seventhly, consult with a qualified electrician for any electrical work. Eighthly, never work on live electrical circuits. Ninthly, inspect electrical systems regularly for any signs of damage or deterioration. Tenthly, be aware of the hazards of electricity and take precautions to protect yourself and others. Firstly, understand the difference between grounding and bonding and their respective roles in electrical safety. Secondly, familiarize yourself with the NEC requirements for grounding and bonding, including the specific requirements for different types of electrical systems. Thirdly, use appropriate tools and techniques for making grounding and bonding connections, ensuring that the connections are secure and have low impedance. Fourthly, inspect grounding and bonding connections regularly to ensure that they are in good condition and have not loosened or corroded. Fifthly, use a ground resistance meter to measure the resistance of the grounding electrode system, ensuring that it meets the requirements of the NEC. Sixthly, use a bonding meter to measure the impedance of bonding connections, ensuring that they are low impedance. Seventhly, use a voltage tester to check for stray voltage on metal parts of the electrical system, and take corrective action if stray voltage is found. Eighthly, use a clamp-on ammeter to measure ground current, ensuring that it is within acceptable limits. Ninthly, use a thermal imager to inspect electrical connections for hot spots, which can indicate loose or corroded connections. Tenthly, stay up to date on the latest changes to the NEC and other applicable electrical codes, and attend training courses to improve your knowledge and skills in grounding and bonding. Furthermore, consider the impact of different soil types on grounding effectiveness and implement appropriate grounding techniques for the specific soil conditions. Moreover, pay attention to the routing and installation of grounding and bonding conductors, ensuring that they are protected from damage and are not subject to excessive stress or strain. Furthermore, consider the use of exothermic welding for making grounding and bonding connections, as this method provides a permanent, low-impedance connection. Moreover, document all grounding and bonding work, including the location of grounding electrodes, the size and type of grounding and bonding conductors, and the results of any testing performed. Finally, share your knowledge and expertise with others, promoting a culture of electrical safety and ensuring that all electrical work is performed in accordance with the NEC and other applicable codes.